In this video, we're just going to talk about 3 different properties that are affected by intermolecular forces. Now, one of them will again be boiling point, so we'll do that at the end. It's going to seem kind of familiar. The first one is something that we have never talked about before, but that you are probably familiar with, and it is called surface tension. If you're not familiar with it from the name, you're probably familiar with it from what I'll describe a little bit later. So, by definition, surface tension is the energy required to increase the surface area of a liquid by a unit amount. Okay, well, that's not very helpful. I'm going to give you an example value. So for water, at room temperature, so this is that elusive 25 degrees, the surface tension is 72.8 millijoules per meter squared. So it would take 72.8 millijoules, that's a pretty low amount of energy, to take water and spread it out over 1 square meter. If you compare that to something like benzene, it is 28 millijoules per meter squared. So water is going to have hydrogen bonding in it. Benzene does not. So benzene is all carbons and hydrogens. So it's going to have just some London dispersion forces holding it together. It's got a few extra electron attraction bits that might hold it. So it might have a pretty strong London dispersion force, but nothing like what you would get from the hydrogen bonding in water. So what this means, the way that you can see it, is that water, if you've ever seen like pictures of water bugs or actual water bugs, like standing on the surface of the water, it's because they're just not applying enough energy to spread those water molecules apart. So that's how they're able to stay on top of the water. Or if you've ever balanced a paperclip on top of water without it sinking, it's because you disturbed it so little, there wasn't enough energy to push the molecules apart. Now, that's something I wouldn't recommend trying it on benzene, but it is something you could not do on benzene because the surface tension is too low. So takeaway points with surface tension, this higher surface tension is seen when IMFs are stronger. And if you have ever accidentally or on purpose done a belly flop into a pool or a lake, this is why it hurts so much. That higher surface tension for water is why belly flops hurt. So you hit the water, you have to put in so much energy to push those molecules of water apart that you get a little bit of a slap back. All right. The next property is something called capillary action. And you've definitely observed capillary action. So by definition, capillary action is the ability of a liquid to flow against gravity. Up a narrow tube. So this is, we think about plants, right? This is exactly how plants get water from soil up to the tops of their leaves. And it's the same mechanism that works if you have ever done a finger prick to do a blood sample. So, right, you get that little ball of blood on your finger, and there's a little tiny glass tube that's actually called a capillary tube. And if you touch it to that little blood drop, it looks like it kind of gets sucked up in there. So the way that this works, there are two forces in combination that allow a liquid to flow up a tube like that. So there are cohesive forces. These are the IMFs, right? These are the forces that hold the molecules together. So this is the attraction of molecules to each other. But there's also adhesive forces. And this is the attraction of molecules to the surface of the tube. So the liquid will travel when the adhesive forces are stronger than the cohesive. So I'm going to draw what will probably be a really bad picture, but if this is our capillary tube, right? So we're super zoomed in, and then we have all of these, say, water molecules down here. What happens is that one water molecule will be attracted to the side. So this water molecule will go up here. Let's get this in a different color. But then it's also still really attracted to the water molecule that's down here. So this one gets pulled up, and now it's attracted. And so this water molecule keeps getting attracted to the side of the tube, and then this one is attracted to this and gets pulled, and then this one was attracted, so it gets pulled. And so the initial water molecules are just attracted to the side of the capillary tube, but the rest of them get pulled along because of the strength of the intermolecular forces. So capillary action is also, and this type of adhesive attraction, is why water has that concave meniscus. So if you were in something like a graduated cylinder and you filled it up with water, you're trying to read it, you're looking at this very bottom part. This is all my liquid water. That pull up to the sides is because of the greater adhesive force. It's just that something like a graduated cylinder isn't small enough to act like a capillary tube. So the water mostly stays down in the bottom, but it gets pulled up just a little bit at the sides. So the last property, and this is going to get carried over into some later videos when we talk about the energetics involved, we're going to talk about vaporization and a little bit about vapor pressure. And this is the same thing as when we talked about boiling point, right? So vaporization is just going from a liquid to gas. It's just a fancy way to talk about it. It means boiling. So what we will see is that if we draw a picture, so let's say I have some liquid, right? I have all of these liquid molecules in here. We'll just pretend that it's water. It could be any liquid. Some of these molecules can escape and turn into a gas. And we will use some things that we learned last semester, and that hopefully you remember a little bit, to explain how all of this works. So vaporization, we are talking about going from a liquid to a gas. When we talk about going from a gas to a liquid, we're talking about condensation. We have done some of this phase change stuff already. In a sample of a liquid, what we will see, well, in a sample of anything, what we should see, if you remember from kinetic molecular theory, is that temperature is directly proportional to kinetic energy. So at a higher temperature, we have a higher average kinetic energy. Now, the individual molecules have a range of kinetic energies, but at every temperature, some molecules have enough kinetic energy to escape the surface. So this is why water continues to evaporate, even when it's not at its boiling point or when it's at lower temperatures. It's because at every temp, some molecules have enough to escape the surface. The trends that you'll see with vaporization is that the rate of vaporization should increase with increasing temperature, right? So liquids evaporate faster if the temperature is higher because more molecules on average have enough kinetic energy to escape the surface. The rate will increase with increasing surface area. And that's just because you have more molecules at the surface. And the rate increases with decreasing IMF strength. So this is the same thing that we talked about under London dispersion forces. If the molecules are easier to pull apart, they will pull apart more quickly. Now we do have two terms. I want to define them just because you will see them come up if you have not already. Something that is volatile vaporizes easily. And if it does not vaporize easily, the opposite of volatile is just non-volatile.